Okay, so let's work this problem. So this is one out of the book, problem 940. So we have this beam, looks like it's got simple supports, loads on the ends, 8 kips, and we want to find the slope at A, and we're going to use virtual work. I probably should add that in there. Okay. So what we're going to have to do first is find the moments in this structure due to the real loads. It looks like we're going to have a moment expression over the first 5 feet, and then a second moment expression from 5 to 15, and then a third from 5 to 20. So let's try that first. Let's find our real moments. To do that, we need to find the reactions first. So we're going to have a reaction at A and a reaction at B. I think I'll shortcut this a little bit. I think you guys can probably see that these reactions are both going to be 8 kips. You could simply sum moments about A or B and find that. But just to save a little bit of time today, I'll go ahead and fill that in. So let's see if we can find the real moments. So these would be the moments equations. So let's find the first moment that happens somewhere here. So if I'm looking at that cut, would you rather work the left side or the right side? I think the left side looks pretty nice. So I'll draw a little free body diagram of that left side with my 8 kip load. We'll make it a distance x. And of course, at that cut, we'll have our moment, which I'll just call it moment 1. So it'll be section 1, section 2, section 3.
Should we do x1, x2, x3?
Right now, I'm just going to do x because I'm starting at the left side and I'm going all the way in our normal x. When we get to section 2 and 3, I think I may change my coordinate system to make the evaluation of the resulting integrals a little easier. So let's go ahead and do this. So if I sum moments at the cut, you can see the resulting equation for equilibrium is not that challenging. I have the moment 1 plus the 8 kip force times x. So moment 1 is just negative 8 kips. Oh, sorry, kip feet. Oh, I messed that up. 8x. And that makes sense. You notice that with this load acting down, this little free end would probably bend down, and that's our frown, which is negative moment. Okay, so the next section I'm curious in is what's happening in here. Do you want to work the left side or the right side? I don't see any advantage to either one, so I'll work the left side. So I'll have my 8 kip force at 5 feet over. I have my reaction force, which is also 8 kips. And then I'll measure to the cut itself, where I'll have my moment, and I'll call this the second moment, or M2. Now, how should we measure this? I could measure it, again, all the way from the left side over to the cut and call that x. Could do that. But I think it's going to be advantageous if I measure from A to the cut and, say, call that x2. Now why? Because x2 will now vary from 0 to 10. So the resulting integral will be easier to evaluate. It'll have limits of 0 and 10. Where if I measured it from the left to the cut, I would go from 5 to 10, 5 to 15, and that'd be just a little more extra calculation at the end. So I can do that, right? Once I set this system up to be measured in this way, when I do my virtual moment, which we'll do next, I have to use exactly the same system. So you can't mix your systems up. So with that said, I can now sum my moments at the cut in this section, make sure it's in equilibrium. So I have the moment at 2. This 8 kip moment is also positive, and it has a distance of x2 plus 5. And then I have a negative moment created by my reaction 8 kips, and it has a moment of x2. So what is the moment 2 equal to? Well, I've got positive 8x2 and negative 8x2. It looks like they cancel. And I'm just left with 8 times 5, which is 40. So this looks like it's a constant moment of negative 40. That sound familiar? No? Kind of makes sense. You look at this couple here. 8 acting down, 8 acting up, equal and opposite. They're 5 feet apart. So that creates a moment, a positive moment couple of 40. So to keep this in equilibrium, this moment better react the other way 40. And it does. Okay, finally we're out here in this next section. So we're looking at this cut. Do I want to work the left side or the right side? I think I want to work the right side. I'm going to cut it there, and here's my positive moment at 3. Now, how do I want to measure this distance?
x3.
I could measure it from the left side all the way to cut and call it x. And then my limits would be from 15 to 20. Or I could measure it from the right edge to the left. And my integration limits would be 0 to 5. I like that.
Should it be 0 to 5?
Yes. I'll call that x3.
So if you went the other way, it'd be what again?
If I went
From left to right?
If I went from left to right, it would just be x. Or I could measure it from B and call it something else. You can measure it from anywhere you want. Why not measure it here? That seems pretty easy. Now, we haven't done this before in some of our other problems because I've always said, write your moments as a function of x. And I told you what x was. You can do anything you want here. You can choose x to be whatever you like. But if I make this assumption for my coordinate system here, it has to be identical for the virtual system. So if I sum moments here, what do I get? Well, my moment in my sign convention is negative. The 8 kip moment force creates a negative moment also. So my moment in 3 is minus 8x3, which looks identical to this one, except the coordinates are different. Okay, so let's slide down here and let me redraw this beam. And we'll do our virtual system. Now for our virtual system, what do we have? We want the slope at A. So I'm going to assume that I have a couple of 1 foot. Remember, why is it 1 foot? We're assuming that it's unitless. So instead of being 1 kip foot, it's just 1 foot. And I'm assuming it's this way, which means my beam would rotate like this, which is positive slope. So I'm assuming this direction for my virtual couple, and if I get a positive answer, it's positive slope. If I get a negative answer, it's going to be negative slope. Now I do have to do some work here because I have a different reaction at A and at B. And although I could probably figure out what those are I think it's best if we just go ahead and calculate those. So if I come back here and sum my moments at A, make sure it's in equilibrium, what do I have? Well, this is a positive couple of 1. This also creates a positive moment of by times 10. So it looks that by is equal to negative 1/10. And then if I sum forces in the y direction, AY is acting up plus BY is acting up. That's it. So it looks like AY is positive 1/10. So I have a counterclockwise couple of 1, and now my two forces are equal and opposite, 10 feet apart, so they create a counter moment of 1 foot. All right, so let's go back through now and get the virtual moments. Now, since we're doing slope, we subscript these with theta to indicate that these are moments produced by a rotation. That doesn't look like a theta, but that's a theta. So now that I've done these 3 systems for my real moments, I have to do the same systems for my virtual moments. So let's go back and look at this piece where I said I made a cut in the x direction, and I have my internal moment now, which I'm calling M1 theta, and I have no loads on it. So what's M1 theta? 0. Well, that's easy. So when I multiply this times the virtual moment, I don't even have to worry about it. 0. There's nothing to integrate. Now we'll go to the second problem, or the second section. So now I have my reaction at AY. AY was 1/10 acting up. And I also had my virtual couple there of 1 foot. And now I'm looking at the moment there, which is M2 theta. This is still 5 feet, and I measured the distance to the cut from A, and I called that x2. So let's make sure that body's in equilibrium. So let's sum moments about the cut and make sure we're in equilibrium. So what do we have? We have the internal moment, M2 theta, positive. We have the applied moment, which is plus 1. And then we have the moment due to the 1/10, which is negative. So the force is 1/10, and the moment arm is x2. So it looks like the virtual moment in section 2 is what? It looks like, x2 over 10 minus 1. Did I do that right? Well, these two moments ought to match at this point. So it says there's no moment here from the first expression. And what's the moment when x2 is equal to 0? It's minus 1, and that matches the applied moment there. Remember, the applied moment makes the moment jump up. So that seems reasonable. In the last section, which is the far right, again, we have nothing applied there. We measured it from the left, called x3, and we had the internal moment M3 theta. Well, what is that? 0. So it's a lot of work, but it's fruitful Because now I don't even have to deal with the integrations from over the first 5 feet or the last 5 feet. I only have to deal with the integration in this intersection. So let's do that. So now my virtual work expression for the slope at A is what? It's the integral from the middle section here. I measured x2 here, so that would be from 0 to 10 of the real moment in 2 and the virtual moment in 2 divided by EI, and I'm integrating over the distance x2. So let's fill all that in and see what we get. So again, integral from 0 to 10. I should have squeezed out my EI, and I will. So the real moment is this. Oh, it's just minus 40. And the virtual moment was x2 over 10 minus 1. Yeah.
Why 0 to 10?
Because I'm integrating from 0. I'm using x2 as my coordinate system. And this equation is only good when x2 goes from here to here, which would be from 0 to 10. So my virtual system was, what was it? I lost it. Oh, there it is. x2 over 10 minus 1. So x2 over 10 minus 1 dx2. I might be able to do this. So we got 1 over EI, integral from 0 to 10. So I multiply that out, it looks like I get minus 4x2 plus 40 dx2, which would be, bring that outside, so this is going to be minus 2x2 squared plus 40x2, and x2 is from 0 to 10. You guys might have to help me with this. So that's negative 200 plus 400 is 200. So it looks like it's 200, and that's going to be kip feet squared over EI. Now this problem had an E and an I. Let's see, I think E was 29,000 and I was 165. So the numerical answer would be 200 kip feet squared. And let's divide by E and I and convert it. So dividing by E, 29,000 kips per inch squared. I was 165. Did you guys have different values in mastering engineering?
Yes, sir.
Eyes were different?
I had like 185.
Okay, so I got 165 on my version. And then converting, I have 144 inches squared per foot squared. So it looks like all my units cancel. So what's that equal to? Looks like a pretty small number.
Yeah, 0.006.
Anybody else get that? Give me more decimals to make sure I have my significance right.
0.06019, and you go to the third significant figure, so
00609.
19, so we 2.
19.
Mastering engineering.
Okay.
You go through 6 things.
And that should be in radians. Do you have to put in the coordinate? I mean the unit?
No.
Yes, sir.
All right, so let me take a. You won't be able to see this on the video, but I'll enter it in. See what happens. 0.00602. Yay! We got it right. So that is correct. I'll put a nice green underline on it. So any questions about this one?
Can you do it in conjugate style?
I'm sorry, what?
How long have you been teaching this class?
How long have I been teaching this class? I started teaching this class in the fall of 1993.
I was born that year.
Sorry. That was a good year, 93.
You saw the amount of work I did versus the amount of work you did. You would say it was pretty bad.
What did you do different?
Well, I did the.
Well, let's talk about this. Even if you had chosen a different coordinate system, the moments at the end should have been 0.
Right.
So all you're left with is whatever you pulled off here and whatever you pulled off here. No matter what you would have chosen here, I think you're going to get minus 40. So it just comes down to what you wrote your equation here. Even if you had to integrate it in x and you went from 5 to 15, the resulting integral would have just been 5 to 15. It would have just been one of them. It would have been an extra calculation. But, the worst case would have been that those first section and the third section were non-zero, and you would have a string of these integrals to do with multiple limits to evaluate. That would be quite challenging. And I probably, with a fairly high degree of certainty, since probability and certainty follows this class, I would not ask you to evaluate that. I'd ask you just to write this equation, which I would call the virtual work equation, and just ask you to stop. However, if the problem really worked itself out to be something like this, then I may ask you to go ahead and finish it because that amount of work is not that challenging. Okay. But for me in this class, this is the most important thing, is dissecting the problem up, creating your real system, keeping the same system for the virtual system. Now, one thing you might want to think about is sometimes in order to accommodate your virtual load, you may have to use a slightly different system than your real system. But as long as the coordinates match, right? We've had problems before where the real moment lasted for a longer period and the virtual one didn't. You had to split it up. So that way you just have to split up the integral to match. So this is really not a bad problem.
So just to be clear, say you would evaluate the right side of the very first, so the middle one, the 10 feet section, you evaluate the right of it, you'd put your unit couple around the pennant B, not the roller A, right?
You're talking about the real moments or the virtual moments?
Right. It says you did the real moment to the right of the 10 feet, the right side.
Okay, let me flip this over. So this is the real moment system that we're talking about.
Right.
So you're saying that if I make a cut here, I work the right-hand side.
Right. Then you apply your unit couple at
No, there is no unit couple.
No, in the virtual part now.
Oh.
You would do the unit couple of B, not A, correct?
No, there would be no unit couple at B. There's only a unit couple at A because that's where I want the slope.
Oh, okay.
There's only one unit, there's only one virtual force or moment. It's at the place you want the thing in the direction you're assuming. So since we're doing slope only, there's only a virtual moment, and it's applied at A because I want the slope at A. And I've assumed it to be positive, and we calculated a positive answer, so the slope at A is positive. Now, does that make sense? Go back to the original problem. Do you think the beam at A should be sloping upwards? Yes. And I think so. That as you push these two ends down, you're going to get kind of a concave shape like this. So yeah, the slope at A is positive. Probably the slope at B is exactly the same value, but negative.
What if you assume?
Then you would have got a negative answer here, which means that this assumption of a positive slope was incorrect.
So for displacement, you just put a regular load.
Right. If I wanted to say, this problem probably has a companion problem that says, what's the displacement at the center point, for example. So my virtual system would just be a unit load at that point acting down. And you'll notice then I would have 1, 2, 3, 4 moment equations for my virtual system.
I don't understand that. Wait, go back.
Would you cut it to the left and right?
Well, let's just look at it this way. If I work the same problem, except instead of wanting to find the slope at A, I want to find the displacement at the center.
Oh.
So what would my virtual beam look like? Well, I would still have my reaction, my supports. Oh, I drew that one backwards. That's okay. You get the idea. So where's my virtual force? Right in the center. So how many moment equations do I have to write? 4.
Oh.
One that's good from this 5 feet, the next 5 feet, third 5 feet, fourth 5 feet. You're probably thinking, ugh. But it's not that bad, because what's going to be the moment out here? 0. So you're only going to have a moment equation from here to here. So 2. And that would match your real moment that's good over the whole distance. So your final analysis, and if I continue to use x2 as my coordinate, I would have one that went from 0 to 5 using the real moment at 2 and whatever my virtual moment is at 2, right? Except I'll have to say it's 2, 1, because it's in 2 sections, right? And then I would have to add another one that might go from 5 to 10, same real moment, but a different virtual moment, say 2. Because I would have one here and one here, 2 different ones. In that problem, I may say, you write those out, you're good enough, you're done. Yeah.
So you got this integral from 0 to 5. Your moment at 2, your real moment equation you took from left side of A, let's call that 0, 0 to 5, and then to x2.
Well, x2 in this case starts at A and goes to B. So that's from 0 to 10.
Mm-hmm.
So I had to break that up. Instead of going 0 to 10, I had to break it up and stop at 5, because that's where my moment equation in the virtual system changes.
Why wouldn't that be from 5 to 10 and then 10 to 15?
Because I'm doing everything in x2, and x2 starts at A. It's
Right.
0 at A.
This is like a datum theory, like you pick your datum
Yeah.
and everything comes from
Exactly. Most of the time in previous problems, I had told you what the datum is. It's X, and it starts at the left edge. You don't get a choice.
Oh.
You can now choose any way you wish.
So what is
You like
so
being
we would
told.
have continued.
What was your question, Mr. Reed?
I was going to say, if we continued to find the displacement, would it have been easier to cut that beam in the middle 2 different places instead of just one? Because we would already had that, right?
Well, for this problem, you would have to cut the structure somewhere here and choose to work the left or the right. Probably the left would be easier. And then over here, you'd have to cut it here and choose to look at the left or the right. Probably the right side would be easier there.
That's what I'm saying. If we did it to find the slope, would it have been easier because we already found?
No. The only thing that's easy is that in all these systems is once you find the real moments, they're found. You don't have to go back and find them again. But each virtual problem presents a different virtual beam, and they require a set of virtual moments, and you need to make sure that they match up so that you can reassemble all the energy and account for it all over the whole length of the beam, no matter where you put your datum. Remember, it's integral, so you don't, as long as they don't overlap or you don't leave a gap, the energy should be the same. Okay? Well, that was a long video, almost 30 minutes, but I think it was probably 2 or 3 problems in one. So, more of a capture of the class more than the problem.